Good morning, this is Paul from All About Digital, and today I'm going to introduce you to my new course called Switching Theory and Digital Logic. Today we're going to talk about number systems, so let's do it. In this video we're going to talk about number systems and conversion techniques. The first goal is to gain a basic understanding of number systems. We're going to understand the use of positional number system representation and how it's used to represent popular number systems. Also, we're going to understand the methodology used to convert between binary-based number systems and the decimal system. So the four most popular used number systems are: number 1 is decimal, number 2 is binary, number 3 is octal, and number 4 is hexadecimal. These are the most commonly used. Now, in the outside world, in the non-computer world, everybody uses decimal. And decimal is considered to be the most common number system in the world. Now, computers don't represent numbers in decimal. They represent numbers in binary. And so in a computer system, the binary system is considered to be either a 1 or a 0. And in a computer system, it's easy to represent because it's either on, switch is either on or off, or sometimes called high or low. High meaning high voltage and low meaning low voltage. So most common number systems represent an integer n as a string of integer elements called digits. So to repeat, a number system represents an integer like 354 with elements called digits. 354 would be the digits. A digit is an integer restricted in value to a definite range, 0 to r minus 1. Now r, the letter r stands for radix, or base of the number system. For example, in base 10, or radix 10, the r value is 10. And so the r determines the base of the system, also the number of digits. So if we have a base 10, and the digits range between 0 and r minus 1, that's between 0 and 9. So the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 digits. So in base 10, we have 10 digits. So the number 352 in base 10, the integer is 352. The digits are 3, 5, 2, and the radix is 10, or the base. The base is 10. In positional notation, when we write a decimal number such as 10, we should really write it as follows. The number is equal to the two digits, digit 1 and digit 2, with a base or a radix 10. So the number 10 in a base 10 would be written as 10 to the base 10. The number 55 in the base 10 would be written 55 base 10. In binary, the number 10 would be written as the number, the two digits, digit 1 and digit 2, or however many digits you have. In this case, we have 2 digits with the base or radix 2 as a subscript. In the binary number system, the radix is 2, and so there are 2 digits, 0 and 2 minus 1, which is 1. So, for instance, the number 100100 in base 2 would be written as such. Now in this one we have 1, 2, 3, 4, 5, 6 digits. The integer has 6 digits. It's a binary number because we have a base 2, so the digits can only be 0, or 1. So this would be 100100 base 2. In general, for any number written in the positional notation, it would be written as the nth digit times r to the n plus ... the second digit times r to the 2 plus the first digit times r to the 1 plus the 0th digit times r to the 0. And that's equal to the number of the base. Now, since r to the 0, anything to the 0 power is always 1, then we can replace d0 times r0 with just d0, because d0 times 1 is just equal to d0. So what I said was d0 times r to the 0 equals, since this is equal to 1, d0 times 1 is equal to just d0. Okay? So this is the equation of any number system with the radix r and the digits ranging between 0 and r minus 1. So that is the general formula for the positional notation. So let's do an example. Let's expand the number 5853 in the base 10 in positional notation. So we would have the first digit right here, 5 times, this is the third digit out, so this is digit 0, 1, 2, 3. So it'd be r to the 3 or 10 to the 3 because we're in base 10. So the radix is 10. So it'd be 5 times 10 to the 3. The next digit is 8. So it'd be 8 times 10, 2, because that's the second digit. 0, 1, 2, second digit. The third digit is a 5 times 10 to the first, because it's the first digit. And the last digit is 3, because it's the 0th digit, d0. So the number is written as 5 times 10 cubed plus 8 times 10 squared plus 5 times 10 plus 3, which is equal to 5,853 base 10. Now you could say this is like 5 times 10 to the 3 is 5,000 plus 800 plus 50 plus 3 is equal to 5853. 5853 base 10. Now, for a binary number system, it only has 2 digit values, 0 and 1, with a radix or the base of 2. Okay? Thus, the number in radix 2 would be represented as follows. There's the nth digit times 2 to the n. Now, it's the radix to the nth power, which is the position of the digit, plus, let's go all the way down to d0, which is the least significant bit or the smallest digit in the number, the least valued digit in the number, and that equals to the number in base 2. Okay? Now, let's look at an example. The number 10010 base 2 is written as follows. This digit right here is equal to the 0, 1, 2, 3. That's the fourth digit when you start counting from 0. So it's a 1 times 2 to the 4th. Then the next one is a 0 times 2 to the 3, plus another 0 times 2 to the 2, plus 1 times 2 to the first power, plus 0 times 1, or 0, just 0. So that is equal to this number right here. And this is how you'd write it out positionally. Now, why are we doing this? Well, let's talk about it. When we want to convert from binary to decimal, the way we do it is first, let's do an example of the binary number that we just showed in the last slide, 10010 base 2. Let's convert that to decimal. So step 1 is expand this number to positional notation. So we look at it, and the first digit, the fourth digit's a 1, so it's 1 times 2 to the 4th. The third digit is 0 times 2 cubed, plus 0 times 2 squared, plus 0, plus 1 times 2 to the first, plus 0. Okay, again, that's equal to 10010 base 2. That's step 1, step number 1. Step 2, again, we're converting a binary number to a decimal number. Step 2 is expand all terms to their decimal values. Well, 1 times 2 to the 4th. 2 to the 4th is 16. 1 times 16 is 16. The next digit is 0, so we put a 0. 0 times 2 squared is 0 times 4 is 0. 2 times 2 to the 1st, which is 2, is 2. And the least significant digit, D0, is a 0. So it's equal to 16 plus 0 plus 0 plus 2 plus 0 equal to 10010 base 2. Now the third step was we sum all terms in base 10, which means you sum them in decimal. So let's sum them all up. 16 plus 0 plus 0 plus 2 equals 16 plus 2 is 18. Thus, 18 to the base 10 is equal to 10010. Okay, that's it. We're done. Let's do another example. Let's convert 1111 to the base 2 to decimal. So as described earlier, there are 3 steps. And the first step is to expand the binary number to its positional notation. So we look at this number right here, and the first digit is D0, the second one is D1, third one is D2, and this is D3. So we have a D3, which digit is a 1, times 2 to the 3, plus a 1 times 2 squared, plus 1 times 2, plus 1. And that's equal to 1111 base 2. Okay, second step. Expand all the terms to their decimal values. Well, 2 to the 3 is 8 times 1 is 8. So the first digit's 8. 2 squared is 4. So we add 4. The third term, 2. 1 times 2. So we add 2. And then the final one is just a 1. And again, that's equal to 1111 base 2. The final step is to sum all terms in base 10. So we have 8 plus 4 plus 2 plus 1 equals 15. So 15 base 10 then is equal to 1111 base 2. And there you have it. Now we're going to talk about fractions. For the first conversion techniques, we were just talking about the integer portion of a number, and now we're going to talk about the fractional portion of a number. So fractions can also be represented in positional notation as follows. The number is equal to, you place the radix point right here. That's the radix point. For decimal, that's the decimal point. For binary, that's the binary point, but that's the radix point. And then all the digits and the number and the radix to the different powers follow. So for instance, the first digit to the right of the radix point is D minus 1 and radix to the minus 1. The next digit is D minus 2, D to the D minus 2, R to the minus 2, plus all the way down to D to the minus n, R to the minus n. So in positional notation, for a number consisting of an integer and fractional part, the positional representation would be the integer part first, which would be dn, r to the n plus all the way down to d2 r2 plus d1 r1 plus d0 r0, which we know is equal to d0, plus, this is the fractional portion right here. This is the fractional portion right here, plus the fractional portion, which is d minus 1 r to the minus 1 all the way down to d to the minus n r to the minus n. For base 10, the number 0.1563 would be represented in positional notation as 0.1563 equals 1, which is the first digit here, times 10 to the minus 1, plus 5 times 10 to the minus 2, plus 6 times 10 to the minus 3, plus 3 times 10 to the minus 4. A binary fraction would be represented in positional notation as, for example, 0.11101 to the base 2 would be equal to 1 times the radix, which is 2 to the minus 1, plus, that's the first one right here. And then the second one, to the right of the radix point, would be 1 times 2 to the minus 2, plus 1 times 2 to the minus 3, plus here's the 0, times 2 to the minus 4, plus 1 times 2 to the minus 5. Let's do an example. Convert 0.11101 base 2 to a fraction in base 10. First of all, we expand the binary number to its decimal, to its positional notation, I mean. Okay, so the first one would be 1 times 2 to the minus 1 plus 1 times 2 to the minus 2 plus 1 times 2 to the minus 3 plus 0 plus 1 times 2 to the minus 4. 3, 4, 2 to the minus 5. 1, 2, 3, 4, 5. Okay. Step 2, expand all the terms to their decimal values. Well, 2 to the minus 1 is 1/2. 2 to the minus 2 is 1/4. 2 to the minus 3 is 1/8. Plus 0. So that's 1/16 and 1/32. So plus 1/32. Okay, so that's the decimal values. So we sum them all in base 10. Okay, so how do we do that? Well, we can convert them to their decimal equivalents. 1/2 is 0.5, plus 1/4 is 0.25, plus 1/8 is 0.125, plus 0, plus 1/32 is equal to 0.03125. Summing all those together, we get 0.90625. So that's base 10 equals 11101.111 to the base 2. Let's do another example. Let's convert 111.101 base 2 to a number in base 10. Now this number has both an integer and a fractional portion, so we're going to do both in this conversion. So let's first expand this binary number to its positional notation. So the first digit is 0, 1, 2, 3, 4, 5. So we have 1 times 2 to the 5th plus 1 times 2 to the 4th plus 0 plus 1 times 2 squared plus 1 times 2 plus 1 So we've done the integer portion right here, and let's do the fractional portion. Plus 1 times 2 to the minus 1 plus 1, plus 0 plus 1 times 2 to the minus 3. Okay, we've expanded it to its positional notation. Now let's expand all the terms to their decimal values. So we have 2 to the 4th, which is 32. 2 to the 5th is 32. 2 to the 4th is 16. Plus 0. Plus 4. And then plus 1. So add in the fractional portion. That's 1/2. 2 to the minus 1 is 1/2. Plus 0.5, which is 0.5. Plus 0. Plus 2 to the minus 3 is 0.125. Okay, so let's sum all these up, and we'll get the integer portion first. 48 plus 7 is 55. So 32 plus 16 plus 4 plus 2 plus 1 is 55. Plus 0.5 and 0.125. So that's 0.625. So it's equal to 55.625. Base 10. So that's equal to our original number, which was 110,111.101 base 2. And there you have it. Now we're going to talk about how to convert from decimal to binary, the integer portion. Now when you consider conversion from decimal to binary, there's two different algorithms, one for the integer portion and one for the fractional portion. The inner portion uses what's called successive division to perform the conversion. Example, let's convert 5041 base 10 to binary. So how we do it is we successively divide the number 5041 by 2 until the remainder is 0. If the last digit of the divisor is odd, a 1 is written. If the 1 digit is even, a 0 is written. Let's look at this example. 5041 base 10, convert it to binary. So we start down here, we take 5041, we divide it by 2. We don't care about the fractional part that comes out in the division. We just look at the integer portion when we divide. So 2 into 5041, actually 5041 to start off with is odd. So we put a 1 over here. And this 1, when we first start, is the least significant bit. Okay? Next, we take the result and divide it by 2. 2520 divided by 2 is 1260. Well, the 2520, the previous result was even, so we put a 0 here. And when we divide 2520 by 2, we get 1260. It's even, so we put a 0. 1260 divided by 2 is 630. Result is even, so we put a 0 right here. Now we divide 630 by 2, we get 315. And the result is odd. Okay, we don't care about when we do the divide, if we get a fraction, we don't care about that. We just ignore it. Okay, so this is odd, so when there's an odd number, from the result, we put a 1. 315 divided by 2 is 157. Again, it's odd, so we have a 1. Divide 157 by 2, we get 78. It's even. We get a 0. And then on up, all the way up until we get to the top here, we have a 1 left. 2 goes into 1 0 times. And it's an odd number. And so that's the MSB, the most significant bit. So you wait until you get to a 0 right here. And then you know you're done. So 5041 base 10 is equal to, starting from the most significant bit, 1 0 0 1 1 1 0 1 1 0 0 0 1. And that's what we have right here. Okay? Now let's do another example. Convert 250 to the base 10 to binary. Again, 250 successively divided by 2 until the remainder is 0. If the last digit of the divisor is odd, a 1 is written. If even, a 0 is written, like we did before. Okay, let's start down here again. 2 into 250. We take the first digit right here as a 0. So it's a 0. The LSB is a 0. 2 into 250 is 125. That's odd, so we put a 1 over here. 125 divided by 2 is 62. Okay. Ignore the fraction that we get when we divide 2 into a 125. 62 is an even number, so we write a 0. 62 divided by 2 is 31. It's an odd number, so we get a 1. Then 2 into 31 is 15. 31 divided by 2 is 15, and that's an odd number. Again, 2 into 15 is 7. That's a fraction again. We don't care about the fractional portion. That's an odd number. And then 7 divided by 2 is 3. Again, a fraction. 3.5, so we ignore the 0.5. And that's an odd number. And then finally, we get a 1. 2 into 3 is just one time with a 0 remainder. And so it's an odd number, so the MSB is a 1. So this conversion results in the MSB in binary as 1 1 1 1 1 0 1 0. 1 1 1 1 1 0 1 0. So 250 base 10 is equal to this number in base 2. Now let's look at a fractional conversion. Fractional portions of decimal numbers are converted to binary by successively multiplying the decimal fraction by 2. If the result is greater than or equal to a 1 is tabulated. If the result is less than a 1, a 0 is tabulated. The fractional portion is then again multiplied by 2, and the process repeated until the fraction is 0 or enough digits have been obtained. So what we're going to find out here is most of the time you don't get an exact result, and we'll show why. So let's do an example. Let's convert 0.352 base 10 to binary. So the way we start out is we take 0.352 and we multiply it by 2, and we get 0.704, 0.704. So because there's a 0 there, the MSB, most significant bit, is a 0. Okay? That's the most significant bit to the right of the radix point. So this is the MSB, and then as we go out this way, we'll get to the LSB. So this is the digit right to the right of the binary point, in this case because we're going to binary. Okay, next we take the result of that multiplication, 0.704, and we multiply that times 2, and we get 1.408. Since we got a 1 right here, the binary digit's a 1. Okay, now we take the fractional portion, and we write it down here. We multiply that times 2, and we get 0.816. And since there's a 0 just to the left of the radix point, we write down a 0. Now we multiply just the fraction that's left, 0.816 times 2, and we get 1.632. Well, since we got a 1 right here, that 1 is written over here. Okay? Again, we take the fractional portion, 0.632, right here, and we multiply that by 2, and we get 1.264. Well, we have the 1 again right here, so we get another 1. 0.262 times 2 is 0.528. There's a 0 right here, so we write the 0 over here. Now we take 0.528 and we multiply times 2, and we get 1.056. All right. So since it's a 1, we get a 1 right here. Okay, so we're stopping right here because, as we'll show, this conversion, 0.352 to the base 10, is almost equal to 0.0101101. So this number right here is not going to come out even. It's like figuring out what pi is. But that's okay. You just go to whatever the accuracy is that you need. And typically inside of a computer, it's the length of the computer word, 16 or 32 bits. This is the number that we got when we did the conversion, the 352 base 10. We got the binary number 0.0101101. Let's see how close we got to 352 with this binary number. How do we do that? Well, let's just convert this binary number that we got back to decimal. So how do we do that? We write it out in positional notation, and then we expand all terms into their decimal values, and then we sum them. Okay, so first of all, let's talk about negative exponents. As we know in math, if you have a 2 to the minus n, that's equal to 1 over 2 to the n. 1 over 2 to the n. The exponent sign changes from a negative to a positive. So, knowing that, let's just write down what each of these terms with respect to the power of 2. This is 2 to the minus 1 is 1/2. And we have 1/4. Next term is 1/8. And we have 1/16, 1/32, 1/64, and 1 over 128. Okay, so now we expand the terms and we write the decimal equivalents of each of the non-zero terms. Okay, so, well, we have a 0 for the first term. This 0 is this 0 right here. We have 1 times 1/4, and 1/4 is 0.25. So that's this digit right there. And then we have another 0 right here. And then we have 1 times 1/16, and 1/16 is 0.0625. And then we have a 1 times 1/32, which is 0.03125. And then we have a 0 right here, this 0 right there. And then finally we have 1 over 128, which is 0.0078125. So we sum all these numbers in decimal, 0.25, 0.0625, 0.03125, 0.0078125, and we get the number 0.3515625. Well, that's actually a little bit less than 0.352. If you rounded this up, it would be 0.352. But it's actually a little bit less, okay? If we added more bits out here to the right, we increase the precision, we would get closer and closer to 0.352. But how many bits are you going to add? I mean, it may never converge. So most of them don't converge, which means they'll become exactly 0.352. So again, how do you decide how many bits digits to generate? Normally it's determined by the register size of the computer processors that you're using. 16 bits, 32 bits, 64 bits, typically 16 bits or 32 bits. Or whatever the accuracy is required by the problem. But you're not going to get an exact number. But close enough is good enough. Okay? Well, does it ever come out perfect? Well, yeah, it does if you pick the right number. So let's pick a number, 0.8125, and convert that to binary. So we do our successive multiplication. So we start with 0.8125 multiplied by 2, and we get a 1. So that's the most significant bit right there. Okay? Most significant bit right there. Okay? So there's a 1. So now we take the 0.625 multiplied by 2, and we get 1.250. Well, there's a 1 there again, so we get another 1. Okay? So then we take 0.250, multiply it by 2, we get 0.5, 0.5, so 0 goes right there. And then we take 0.5, this 0.5, multiply that by 2, and we get 1.0. And you get a 1, and so the 1 creates an LSB. So, as you are successively multiplying, if you ever get down to 1.0 at the end, 1.0, it's exactly equal to that number. Remember when we got back down to here, when we were dividing? We got 1.056. If we would have got a 0 down here, it would have been the exact conversion. But since right here, and so it wasn't. But right here, we get a 0 at the end here, 1.0. That 0 indicates that's an exact conversion. Okay? So then we can say that 0.8125 base 10 is equal to 0.11012. Exactly equal to. So it's exact. In the real world, it occurs rarely. Let's do a conversion from decimal to binary fractional. Okay? So we want to find a number in base 2. Okay. For the fraction 0.90625, which is in the base 10. Okay, so what do we do? Well, since it's a decimal to binary fractional, we do successive multiplication. So let's do the first multiplication. It's 2 times 0.90625. That equals 1.8125. So we have a 1 right here. So our MSB is a 1. This is our MSB. Okay, let's take what's left over, 81. We ignore the 1 now. Let's just take the fractional portion, 8125. Multiply that by 2. That equals 1.625. And since there's a 1 again right here, that 1 will go over here. That's our next bit. We take the fractional portion, multiply it by 2, 0.625. That's equal to 1.25. Again, there's a 1 there, so there's another 1. This 1 translates to a 1 right there. Okay, so now we have 0.25, so we go 2 times 0.25, and that equals 0.5, so we have a 0 right here. Then we take 0.5 times 5, and we get a 1.0, and that 1 goes over here. Okay, since this is what we got, 1.0 at the very end here for the LSB, we have an exact conversion. Okay, so because this turned out to be a 0. So the conversion result is 11101. So put that up here. 11101. I'm sorry, 0.11101 to the base 2 is exactly equal to 0.910. And it's exactly equal to because the result at the end here came out to be 1.0. So, I mean, think about it. You could just keep multiplying 0.0. So the bits would be 0, so it's exact. Okay. Now we're going to talk about octal numbers. Octal numbers are base 8, and they're commonly used to represent information within a digital computer. Some of the first computers that came out in the 70s, like the DEC PDP-8, exclusively used octal representation to represent binary numbers within the computer. They used a 12-bit mini computer, which lended itself very nicely to octal. So, an octal number can be represented in positional notation, just as we discussed before with other radix or bases. In the octal system, it's base 8. So the numbers are like d to the n, the nth digit, times the radix, which is 8 to the nth power, all the way down to the least significant digit, which would be d0, 8 to the 0. But as we showed before, 8 to the 0 is equal to 1. It's equal to 1. And again, anything to the 0th power is equal to 1. So the general formula for octal number and positional notation is d to the n, 8 to the n, all the way down to d0, and that's equal to the number and positional notation to the base 8. Now the digits range between 0 and 7 because we know that the number of digits in a base system is 0 to the radix minus 1. And the radix is equal to 8. So the number of digits are 0, the digits are 0 through 7 for 8 digits. Okay, octal numbers, this is the chart of octal number representation with respect to decimal and binary. We can see that the octal number starts at 0, and then it goes to 1. So it follows and tracks binary all the way down to 7. So decimal 7, that's the maximum digit in octal. So just like in decimal when it gets to 9, in octal when we get to 7, it's going to roll over to 0 and 1 carry bit. So it's going to go 0 through 7, and then start with 10, 11, 12, 13, 14, 15, 16, 17 octal. And in fact, after it hits 17, it's at its maximum digit value, which is a 7. It's going to roll over to 20, base 8, and then 21, 22, 23, 24, 25, 26, 27, and now it hit its maximum digit, so it's going to roll over. It's going to roll over to 0, and that's going to go to 30. So we go to 30 base 8, and then we go from there, we go 31 all the way down to 37, and that's going to roll over to 40 base 8. Okay, how do we convert between binary and decimal? How do we convert between octal and binary? And the way we do it is we just group the binary digits in groups of 3 binary digits, and those 3 binary digits equal 1 octal digit as follows. For instance, the number 763 base 8 can be represented as 3 ones, which is a 7, 110, which is a 6, and 011, which is a 3. So 111, 110, 011, by grouping the binary digits in groups of 3, you can generate the octal number, which is 763. Therefore, to convert from octal to binary, simply convert each octal digit to its binary equivalent. Now, in the other direction, to convert from binary to octal, group all the binary digits in groups of 3, then replace each group with its octal digit. Let's do an example here. To the right, I have a table which in orange describes the octal digits and the binary equivalents for those octal digits. So the example here says we want to convert this binary number to octal. So let's rewrite this binary number, 1, 0, 1. I'll do a little bit of a separation here. And we have 1, 1, 1, 1, 1, 1, and then we have 1, 0, 0. Let's make this one a little bit longer here. Okay, so we've grouped them in groups of 3. We have them in groups of 3. Let's group them. Okay, and we want to start with the LSB first, which is on the right-hand side. And the reason is because it doesn't always come out to an even number of digits on the left-hand side, because some numbers are represented as integer inside of a computer register, and some numbers are represented as arithmetic numbers, and this most significant bit will be a signed bit. So we want to start from the right-hand side. 1, 0, 0 in binary is a 4. Right here, it's a 4. 1, 1, 1 in binary is a octal 7. And 1, 0, 1 is an octal 5. So this number right here, 1, 0, 1, 1, 1, 1, 1, 0, 0, base 2 is equal to 574 base 8. Okay, hexadecimal numbers are base 16 numbers, or radix 16 numbers. In other words, they have 16 unique digits, 0 to 16 minus 1. And it can be represented in positional notation, just like we talked about before. The nth digit times the radix, which is 16 to the nth power, plus all the way down to the second digit, times 16 squared, plus d to the 1, 16 to the 1 power, plus d0, 16 to the 0. Of course, 16 to the 0 is equal to 1, like we showed right here. Okay, with the digits ranging between 0 and f. Okay, we're going to talk about there's 16 unique digits in hexadecimal. We'll talk about the letters that make up 10 through 15. Okay. So here's the chart that describes the hexadecimal digits with respect to octal, binary, and decimal. Okay, as you can see, there are 16 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now when we get to 9, we need another unique digit. So we start with the letters A, B, C, D, E, F. So that's the final digits that make up the hexadecimal number. So the binary numbers go from all zeros to all ones, and the decimal equivalents go from 0 to 15. Let's look at an example here. Hexadecimal numbers can be converted to binary and vice versa very easily, because just like octal, hexadecimal numbers can be converted by grouping 4 binary digits. Now, octal, you group 3 binary digits. In hexadecimal, you group 4 binary digits. For example, the number AB6, base 16, can be represented as the 6 is 0, 1, 1, 0. Zero, 1, 1, 0 is 6. 1, 0, 1, 1 1, 0, 1, 1 is B. And 1, 0, 1, 0 1, 0, 1, 0 is A. So AB16 can be represented as 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0. So these two numbers are equivalent. So this is the base 2, and it's equal to A, B, 6, base 16. Okay, therefore, to convert from hexadecimal to binary, simply convert each hexadecimal digit to its binary equivalent. And that was fairly easy. To convert from binary to hexadecimal, group all binary digits in groups of 4, then replace each group with its hexadecimal digit. Okay, let's convert a binary number to a hexadecimal number. And we'll use this chart over here. Okay. So here we go. Here is the binary number. I'm just making this up. 1011, 1111, 0101, 1010. Okay, this is the binary number that we want to convert to hexadecimal. Well, the first thing we do, and I like to group from the LSB to the left to the MSB because in some arithmetic numbers, if it's not an integer, if it's an arithmetic number, the most significant bit could be a signed bit, depending on the representation. So we'll start with the rightmost, or the LSB digit. So 1010, let's go down and find 1010 right here. That's an A. Okay, so we have an A. Let's group the next 4. We have 0101. So let's go to the chart and look for 0101. That's a 5. So let's write down a 5. The next 4. Well, the next 4 are 1111, and 1111 is an F. And the final one is 1011. 1011 is a B. Okay, so this number up here, 1011, 1111, 01001, 1010, base 2 is equal to, this is a B, is equal to B, F, 5, A, base 16. So you can see why, rather than write everything out in binary, this is how it's stored inside the computer, inside of a register, or in memory, or wherever it's stored. It's stored as a binary number, always inside the computer. However, when you want to represent it, have a tabular representation, it's much easier, a lot less writing, to write it down in hexadecimal. BF5A. It's much easier, base 16, than binary. And there's an easy direct conversion between the two. Okay, in summary, we have shown how the binary number system, base 2, relates to other number systems such as the octal number system, the hexadecimal number system, and the decimal number system. Also, we demonstrated how to convert between number systems, both integer portions and fractional portions, using the positional number system notation.